Physics. It's Friday, that's February the 9th, and today the lab is due, and that lab was on the ball rolling down the channel, and we had to calculate the work done by friction. So if you would hand your lab to Mr. DeBloom or have it in my mailbox sometime today, I will get it from there. So please take care of that, and or you could have electronically sent it to me by now. All right, we're starting a new mod. I guess we're up to mod 9, and so it seems that there's this burning question in the mind of all physicists and physics students, and that is, why is it that I throw a paper wad at the glass, say, test tube? I throw a paper wad at the test tube with all my force, and it doesn't break. But with the same force, I use a hammer on the test tube, and it does break. So why does that happen? The answer to that question lies in this mod, and the topic is momentum. Alright, so the word momentum is the sum of two products. Momentum is mass times velocity. So we have to come up with a letter to represent momentum, and we decided that M was not a good choice because it's used so often for mass as it is in the very momentum equation. So we had to look around for a better idea, and it turns out in Latin the word momentum is this. I don't know how to say that in Latin. You guys have had your Latin, I think. So, patere, I don't know. That's my feeble attempt. But I do know that it starts with the letter P. So, we are going to call momentum P. From its Latin roots, patere meant to go forward or rush. So, momentum, similar. So we're going to call it P equals mv. Our first equation for this mod is upon us already. Is it a vector or a scalar? So we're wondering, is this a vector or a scalar? And you are taking notes now on your day one papers. If you don't have those yet, get those and catch up. All right, momentum is mv. We call it P for momentum equals mv, and we are discussing, is it a vector or a scalar? And the answer to that is hidden inside of here, because we already know if this is a vector or a scalar, and we know if this is a vector or a scalar. So mass does not show direction, so its scalar velocity is a vector. Therefore, if we multiply a scalar times a vector, you're probably suspecting that momentum is also a vector. Right, because of this relationship, once we have a vector on this side and a vector on this side, since they both have size and direction, the velocity and the momentum vector will always point in the same direction. So velocity and momentum will always have the same direction. All right, and that you can see from the equation. We have these sides equal. Mass doesn't have a direction, so we're going to have to match the direction of these two. So if I drew a scenario like this, say I went, say this is a mass I mean, that's a momentum, and this is, I'm sorry, yeah, momentum, and this is velocity. Could that ever be possible in the same action? And the answer is no, that's not possible, because momentum and velocity vectors are going to be in the same direction. So could it be like this? Imagine those are parallel. I don't have an eraser. So imagine these are parallel. They are in the same direction. Could it be like this? The answer is no, because we see here that momentum is the larger one because it's equal to the velocity times some number, the mass. So this is the short one. When multiplied by a number, it becomes equal to the longer one. So, nah. So we've got two no's. Let's come up with a yes. So I'm going to have the larger one, and that's my momentum vector. And the shorter one in the same direction is going to be my velocity vector. Oops, I messed up here. I'm sorry. This is supposed to be a V. Alright. Two hands up. So the velocity vector is going to be longer. I mean, it cannot be longer. Mass is the same, but mass doesn't show direction, so it made no sense to call that mass. Alright, so this is the correct scenario. In the same direction, momentum longer than velocity. Let's talk about the unit. So we have momentum equals mass times velocity. So the velocity unit and the mass unit are going to come together. So what is the unit for mass? Can you tell us, Kevin? Are you here today, Kevin? It is kilograms. Good. All right, how about velocity? So it's meters per second. If we're going to deal with the metrics, like I started with kilograms. So we get kilogram meters per second. Kilograms times meters over seconds. And guess what? We did not rename it because, of good reason, we're waiting to save the rename of this unit. Right, for now, if we have a momentum, we're going to call it a kilogram meters per second. But we're waiting to see if it's going to be renamed an O'Neill, a Wilhelm, a Cord, a Stone, a Stirling, or a Cappelletti. All those names are in the running to rename the momentum unit when you make significant contributions to physics in the future. So right now, it is not renamed. So it's just what it is. So, alright, I hear two dogs barking, and looking out the window, I see that the two dogs have something in common. Pretty much the same mass, but differing momentums. Is that possible? How is that possible? How can two dogs with the same mass have differing momentums? Well, recall that momentum is mass times velocity. They might have the same mass, but they must have differing velocities. All right. Woof woof. I hear two more dogs. This time, they have the same mass, and they have the same speed. Yet, these dogs, smart dogs, claim they have the same, no, they have differing momentums. How can this be? Alright, I'll let you answer that. How about you, John? How can two dogs running down, we're looking out the window, they're running down the parking lot, they have the same mass and the same speed. How could they have differing momentums? John? Because they have differing directions. Remember, momentum includes directions. So even though they have the same speed, that's why I didn't say velocity, I said speed, because speed is only the numerical part, it's not the angle. So two dogs can have the same speed, the same mass, and differing momentums because they have differing directions. Alright, I can't fool you. So, somehow you must remember that momentum equals mass times velocity. And that it would be nice if there was a V in the word. How about we make this a V? Now we see it, mass times velocity. My little memory aids, which usually helps no one. Alright, so on this side of the paper here, the big idea is momentum equals mass times velocity. So we'll have some problems to do in a few minutes that will exercise that formula. So hang on to your socks. Alright, so I'll show you what one's like when we get to this one. Let's see if I can get it in the screen even. There we go. So here it says the mass of a, I'm sorry, this is not mass, this is a force because it's a Newton. And Newtons, remember, if you forget what unit force is, I will force a fig Newton into your mouth. So a Newton indicates that we have a force, but we can get mass because weight equals mg. A 45 Newton child runs down a road. If the child's momentum is this, what is the child's velocity? So you're going to pull out the formula P equals mv. You're going to calculate mass from the weight, and you're going to, they give you the momentum, and you'll just solve for v. And you'll have several problems to do. But I wanted to introduce another useful equation. So this time we're going to start with an old friend, a force equals ma. And force equals ma is going to be replaced because acceleration is what over change in time? This was like mod 1. Mod 1, what change in what over change in time is acceleration? Dimitri? Change in velocity over change in time. Very good. So, I'm going to replace A in this formula. Thusly, change in velocity over change in time. So, I'm going to multiply both sides by change in time. Force, change in time. Now that disappears from the left, from the right, and appears on the left, and I have mass change in velocity. But another way to write change in velocity, which is helpful, is if you have a change in velocity, that means you had a starting velocity and an ending velocity. So you're going to have to subtract the final one. Subtract the initial one from the final one. So change in velocity is velocity final minus velocity initial. And now I'm going to distribute the m. Alright. And at this point, I recognize that I have an mv here and an mv here, and that is momentum. So we have a final momentum minus an initial momentum, so we can call it change in momentum. So going to put the change of momentum here on the left. Let's do a switcheroo. And this is the helpful equation that will guide the rest of our problems for today. So change in momentum equals force times change in time. Sometimes I call that the fat equation because it sort of looks like the word fat, but that's just my rendition. Don't try that with any other teacher or physics course. All right, so it turns out that all our Little League baseball, and if you played softball similarly, all of those coaches know this formula, because when you're at bat, you want more momentum. You want the most you can get. So we want a lot of momentum. So as the ball comes towards you, our job is to send it back with the bat. When the pitch comes towards you, you're going to send it back with as much momentum as you can. So you have two things that multiply together to give you that large momentum. But let's say you're swinging with your maximum force, and you can't really swing any harder. So it turns out that all our baseball and softball coaches know this formula, because they would go nuts about this, because they knew if this could be maximized, if we could increase that, then we would have a larger momentum, which is the goal, the whole hitting the ball. So how can we increase the change of time? Kevin. All right, the ball's coming in, and it's going to hit the bat, or the bat's going to hit the ball, hopefully. Well, I have seen the ball hit the bat, but it's not the best hit. So the ball is going to be hit by the bat with all the force that the hitter can muster. So how can the hitter increase this time of contact when the ball hits the bat? He can follow through. Follow through is when you hit the ball, but you continue your swing after the ball is hit. And just that motion of that continued swing all the way around seems like it might be a waste of time, because you need to drop the bat and run to first base, but it is not. It is going to, it will increase the change of time of contact, that follow through. So if you were a poor hitter, it may have been because the ball came, as soon as the bat contacted the ball, you dropped the bat and you had no follow through. But a follow through will increase the change of time. That's with a contact between the ball and the bat, and the force is at a maximum. You're swinging as hard as you can, and then you'll have the maximum momentum. All right, let me do two examples, and I'll set you off into your work. All right, here we go. Some of your problems today will use this fat equation. And the first one I'll do is a golfing. A lot of sports deal with momentum, you'll see. So we have a golf club and a golf ball, not drawn to scale. It's a .100 kilogram golf ball. It is going to be launched at 30.0 meters per second at an angle of 45 degrees. And I want you to find the force in this scenario. Find force. So, obviously, if we're looking for force, we must know this and we must know that. So to see the change in momentum, it'd be better to write it mv final minus mv initial. Right down here, mv final minus mv initial. So that is the same as the change in momentum. So I'm going to write it that way so I can get my values easier. Force is what I'm looking for, and change in time, I had to give you. So let's say that the contact time is known and it's 0.112 seconds. So force is what I'm looking for. I know time is 0.12. Mass is given as 0.1. Velocity final is given as 30 minus mass. What's the initial velocity before the ball is hit? The initial velocity is 0. So this term has no consequence to our work. So we have a 0.1 times 30, so that's 3 equals 0.12 times force divided by 0.12, sig figs of 2. It comes out to 25. Since it's a force, we're in newtons, and because it's a vector, it's going to have the same direction that was in the problem. The velocity vector, the force vector, is going to be at 45 degrees. So there is a problem, and you'll be asked to do similar ones in a second or two. Let me give you one more. We'll stick with the sports scenario. Back to baseball. Here's a glove, poor rendition of a glove, and it is stopping the baseball. The baseball is 250 grams, and the force of the glove is actually creating a force as the ball hits it, and that force of the glove is 55 newtons, and the speed of the ball when it's hitting the glove, velocity of the ball, is 22.1 meters per second. So let's see if I can get that in a little better. A little better there. All right, and I want you to find how long does it take for the glove to stop the ball? How long to stop the ball? All right, so let's check that out. Anything with time is going to use our FAT equation. So we see time in this problem. And how long is time? So again, that's what we're looking for. No, the other one was force. So this time we're looking for time. I'm going to switch again to change in momentum the way it was in the other problem. MV final minus MV initial. Momentum final minus momentum initial is the same in change in momentum. The force and change in time, which is what we're looking for. Mass is known to be 0.250. Velocity final. When this ball is coming toward the glove with this velocity, but at the end of the problem it is still. So velocity final this time is 0. So it depends on the scenario. The mass is 0.250. So I've got this, and now I'm here. Got that. And what's the velocity initial? Given in the problem as 22.1. Now I'm going to go over to the equal side, and it says the force that the glove exerts is 55, and find change in T. Alright, so this is gone. 0.250 times 22.1 is 5.53, and that equals 55. Change in time, divide by 55. And I get the change in time is 0.10 seconds. Alright, that's how much time it takes for the glove to stop the ball. Alright, you will be using these formulas to do these problems. That's the momentum worksheet. So, pulling out again. We already mentioned that this one is P equals mv. Here we have momentum and velocity, so P equals mv. But here we have the fat equation. So you're going to use that equation similar to what you just saw with my examples, and this one and this one. So the first two, you'll use P equals mv. The last three, you'll use change in momentum equals F times change in time. On the back is for another day. So you'll be responsible for number 1 through 5. So work on those in class. If there's not time to finish them as an assignment. All right. That's it. Carry on, class. Goodbye.